We continue our study of modules or representations of a semi-simple Lie algebra G over the complex numbers. So the modules or representations we study are such that if we act with the raising operators, at some point we will find 0. So these modules have kind of like highest weight vectors and can be schematically sketched as such. So in these modules, we want to find some structure, and we do this by studying the action of the center of the universal enveloping algebra, Z. So this is the center of the universal enveloping algebra of G. And we'll study the action of the center on such representations. Now, it is clear that if we have a highest weight module with a single highest weight state of highest weight lambda, then if we have a Z, an element of the center, it must act to multiply the highest weight vector, and we call the multiple chi lambda of Z acting on V lambda. And then this so-called character which is a map from Z of G into complex numbers. This character is the same for all of the vectors of the highest weight module. Moreover, the kernel of this character, which we call the central character, is a maximal ideal of Z of G, and chi lambda is an algebra homomorphism, as can easily be checked. So we have some action of center elements on our highest weight module of highest weight lambda called chi lambda. Then we can study a projection map which projects the universal enveloping algebra onto the universal enveloping algebra of a Cartan subalgebra of G called H. And the projection is such that, well, we first write the polynomial in U of G in terms of some PBW form where we have all the raising operators on the right, and then we set all raising and lowering operators to 0, and we find some polynomial in the variables H. So this is the projection map. And if we restrict the projection map to the center of the universal enveloping algebra, this is called Xi, and it's called the Harish-Chandra homomorphism. Now let's recall the dot action of the while group on weight vectors. So how does that work? We have W, an element of the while group, acting on some weight vector lambda. What is it? It's just W, ordinary W, acting on lambda plus rho minus rho, where rho is half the sum of the positive roots. So this is the dot action. And it's important because, in fact, we have the property that the character of lambda and the character of mu are equal if and only if there is a dotted while action which links mu and lambda. So in this case we say mu and lambda are linked. They are in the same linkage class, which is the orbit of this dotted while action. So this is a very important property. The characters are the same if the highest weights are linked by the dotted while action. Now we can identify U of H basically with the polynomials in H. And because of the dotted while action, it's interesting to define an action on the polynomials, P of lambda, which sends them to P of lambda minus rho. Now we can shift or twist the Harish-Chandra isomorphism, homomorphism, by this shift, and then it looks like psi, which is the shift acting after psi, which was this projection map restricted to the center. So then we can define we can see that the character can be identified with lambda plus rho after psi of z. So let's do an example. Let's consider SL2C. We identify H star with C. We have that lambda is identified with lambda of H. Then we have a central Casimir element, which is C2, which is nothing but 2xy plus 2yx plus h squared, which is equal to h squared plus 2h plus 4yx if we write it in PW form. So then, after forgetting the x and the y, as well as twisting, we get h minus 1 squared from the first term twisted plus 2h minus 1 from the second term twisted, because we have to recall that rho is basically 1. Size z is therefore h squared minus 1, which we know to be Weyl symmetric, because the Weyl group will map h to minus h. So this is a Weyl group symmetric polynomial. And if we compute chi lambda of z, it is lambda plus rho evaluated on h squared minus 1, which is basically lambda plus 1 squared minus 1, which is lambda times lambda plus 2. So therefore, for SL2C, we have that lambda and mu are linked or in the same linkage class if and only if lambda is mu or lambda is minus mu minus 2. These are the linked weights, and this for all lambda and mu. Now here are 3 properties shown by Harish-Chandra. Psi is an isomorphism if it is considered from CG to the polynomials on H, which are Weyl invariant, then this is an isomorphism. The second property is that when the characters are the same, if and only if lambda and mu are linked. So there is a W such that. And the third property is that every central character is of the form chi lambda. So every maximal ideal is of the form chi lambda, where lambda is some highest weight. So these properties of weights and of highest weight representations are a first step in understanding the category of all modules of all representations with a highest weight structure for semi-simple Lie algebras G.